All right, well, I will begin.
Let's see how much I can get on the word before he actually comes.
I will begin. All right. Dearly Father, we thank you for this day. Thank you for the students. Pray that you'd just guide our thoughts and our steps today. Help us to glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. Are there any CFARs here? No. The camera person's using active cloaking right now, so don't look too hard. Bradley will eventually return. Let's see here. So I'm going to stay on this board for a bit. Let's see here. We're on lecture 10, which is on isomorphism. All right, so in this lecture, I'm going to use the following notation. If I write, say, G and star, all right, this means we have a group G with operation star, all right. This kind of notation is important because I'll be talking about more than one group, all right, and more than one operation. So let me just get to the first definition here. So here we go. Definition. Phi, a function, all right, from G1, comma star, to G2, comma sharp, all right, is a homomorphism if and only if phi of x star, let me use A and B for a second here. Phi of A star B is equal to phi of A sharp phi of B for all A and B in G1. All right, Mr. Hoogerworth. I started it. All right. So this is the definition of homomorphism. Does this? I mean, I know it's kind of funny looking at the moment, but I would just make a remark that this is very much analogous to, what's this like? We had in Math 321, we looked at T from, say, V to W, right? And we had something like T of x plus y equals to T of x plus T of y, right? For all x and y and v. What did that make T? It was a linear transformation, right? So the concept of homomorphism is much like the concept of linear transformation. It says that the operation on G1 is in some sense transported to the operation on G2 in the natural way. It's structure preserving. Okay, so a proposition we have, my first proposition, right over here, proposition 1, is that if phi is, like we just said, G1 star to G2 sharp, a homomorphism, and if E1 is identity on G1 and E2 the identity on G2. So if you have all this, right? then what? Punchline. Then phi of E1 is equal to E2. In other words, this should not be terribly surprising. Of course, remember for linear transformations, we have t of 0 is equal to 0, right? So I'm saying that that keeps happening even when we're dealing with additive identities, when we're dealing with multiplicative identities, or identities with respect to composition, or identities with respect to all kinds of wacky, weird group operations that we don't have names for. All right. Okay, so we have to prove this proposition with the tools at our disposal, which are just axioms of group and definition of homomorphism at the moment, right? And so, let's see if I find my markers. So let's see here. Proof. Any questions before I get into the proof? What does it mean, by the way, to have E1 the identity? It means that E1 star x is equal to x is equal to x star E1, right? For all x in G1. We know that, right? And what else do we know? E2 sharp y is y sharp E2 for all y in G2. These two things were given. That's what it means to have the identity in G1 or the identity in G2, right? All right. So let's look at this. Number one, I would point out to you, if we look at phi of E1, all right, sharp E2, what do we get? Just think of y equals to phi of E1. What does this give us back? Phi of E1 again, right? So that's my observation number one. Two observations. What's my second observation going to be? Well, we know that E1 star E1 is equal to E1. So that implies what? That implies that phi of E1 is also equal to phi of E1 star E1, right? Because those are equal. But then by the homomorphism property, which I'll do in blue, what do we got? Phi of E1 sharp phi of E1. I'm suffering through these stars and sharps because the only problem I've graded so far in the test is problem 1. All right? Because I have been sick. I'm still sick. I don't know when I'm not going to be sick anymore. Anyway, it's just my new normal. So I should just accept it, I guess. Be a good Democrat. But, sorry. It seemed unnecessary. But, you guys, like, half of the definition is in juxtaposition notation, but then the other half is in star. And then, like, it's some sort of random. I've got people with equations that involve both juxtaposition and star. It's like you're writing the definition of group. You got to make a choice. You're either going to commit to juxtaposition or you're going to commit to star, but you can't like mix and match in the course of a definition. Like that is not kosher. To quote my community college professor, that dog will not hunt. Let's see here. So, all right. So we then thus we have phi of E1, right? Is common. It's equal to what? It's phi of E1 sharp E2, but it's also equal to phi of E1 sharp phi of E1, right? So by the cancellation law, what do we get? By cancellation, or multiply both sides on the left by phi of 1 inverse, phi of E1 inverse if you like, right? No, I'm just going to get to the point here. So thus E2 is equal to phi of E1. Done. All right. let's see here. Let me just make a comment on notation. So suppose we have G1, we have G2. Over here is the structure preserving preservation condition. All right, so start out with the easy one, plus and plus. We have phi of A plus B is phi of A plus phi of B. That's how it works, right? What happens if we have juxtaposition on this on this side? What's juxtaposition mean? It means we express the product just by putting them next to each other, by juxtaposing them, right? This is juxtaposition, and then that is equal to phi of A plus phi of B. All right? Of course, you can do the other way, right? These are all flavor options for homomorphism. Composition, right? And then composition over here. That would be something like phi of, say, F composed with G is phi of F composed with phi of G. Of course, if we're working with permutations, the composition is often omitted. The symbol composition is omitted. We just use juxtaposition to denote composition in the context, for example, of cycles, right? So anyway, there's lots and lots of different cases contained in this abstract idea, right? And that's why this proof over there is really kind of staggering when you think about what we're doing. Why do we abstract things? You know, you're like, well, this is the 10th lecture. You're finally going to talk about it. Great. There's a simple and obvious reason. If we can identify a common structure to hundreds of different examples, right? When we prove something with respect to the structure that unites them, we have proved it not for one example, but for all of those examples, all at once. And that is part of the power of abstraction, right? That over there shows you that it sends the identity to the identity, no matter what the particular quirks of the groups we're looking at are. Right.
So we abstract so that we don't have to spend eons proving examples.
Right, we abstract for the sake of efficiency is one thing. No, it's more than that, but yeah, that's part of it. Okay, so some examples. I have 3 examples. Example 1. We could let phi1 of x equal to e to the x. All right? And here phi1 is going to be a function from the reals to where? You can tell from my formula. It should take you back to the days of your youth. Pre-calculus, whatever. What do you say? Fine. I have to do all the work. Fine. Positive reals, right? Or if you like, we could say r greater than 0. Something like that. So this, what's the group structure here? So to be more pedantic about this, it's from the reals under addition to the positive reals with multiplication, right? Although I really hate to use multiplication like that, so I'm going to use a dot. Sorry. All right, so is that true? Well, let's see here. Phi1 of x plus y is e to the x plus y, which we know is e to the x times e to the y, right? Which is, of course, phi1 of x, phi1 of y. There you go. We have the structure. Is it a function? It's a function. All right. Have we proved it's a function? No. I'll leave that to the real analysis course. Fine. Yeah. And then how about this proposition we just did? What's the additive identity in R? It's 0, right? And that goes to e to the 0, which is equal to 1, which is, by the way, the identity in 0 to infinity, right? Multiplicative group. So there you go. That's an example of a homomorphism. The exponential is a homomorphism. Another example, a little bit more exciting. Phi2, I'm going to define a mapping from the general linear group n by n matrices over a field to the non-zero elements in the field. I think Gallian tends to use F asterisk for this, but you can forgive me if I use that because that's what I've been using. And the formula here, phi2 of A, guess what? We're going to use determinant of A. Right? So the determinant of A is a number, right? If you look at a matrix formed by n matrix with elements from a field F, that gives you an element of the field, right? And if it's an invertible matrix like this, in fact, by definition, this is non-zero, right? So that shows you that this mapping is into here, right? So it's a well-defined map. You missed the test earlier this week. Oh, you're CFA? No? Oh, you're just sorry. Okay, good. Sorry. Welcome. We were debating whether a CFA person would come to this class. It happened. Awesome. All right, so phi2, are you planning to be a math major?
Yes.
Oh, excellent. As best major here. Good choice. Let's see here. Determinant. Forget about engineering. Okay. Let's see here. So that goes for you guys too, you double majors. Sorry, Jess. So determinant, phi2 of AB is determinant of AB, right? But we know properties of determinant. In fact, they're true for an arbitrary field. If this makes you uncomfortable, you can write F equals to R if that makes you feel better about your life. But the example is more general than that. So determinant of A, determinant of B, property of determinants. And then that is phi2 of A, phi2 of B. So therefore, phi2 is a homomorphism from the general linear group of n by n matrices over a field to the set of non-zero numbers in the field. Okay. Example 3. I'm going to define phi3 to be a mapping from the symmetric group of order n to Z2. Right? So Z2, remember, is 0, 1 modulo 2, right? Let's see here. And what we're going to do is we're going to say phi3 of a cycle sigma is equal to, I'm going to define it case-wise. It's going to be 0 if sigma, and it's going to be 1 if sigma is what? Fill in the blank for me. I'm dividing the symmetric group into two pieces. What are the two pieces I'm probably using? Even or odd, right? So the alternating group or not in the alternating group. In other words, even or odd. Right? So if we look at phi3 of sigma beta, right? You can check, looking at cases, that that's this plus that. I guess there are 4 cases to consider. If you have even and even, right? Product of 2 even permutations is an even permutation, right? And that gives you 0 plus 0, so we get 0 equals 0. If phi is even and beta is odd, then we have in total an odd permutation. So the left-hand side is 1. And the right-hand side is 0 plus 1. And then you get 1 equals 0 plus 1, 1 equals 1 plus 0, and finally, if phi and beta, sigma and beta, are both odd, then, of course, their product is even. So the left-hand side would be 0, and the right-hand side would be 1 plus 1, which is also 0 mod 2, right? So there you go. That's a homomorphism. All right. Questions? So here's some examples for you. So I now introduce definition. I suppose I could define this for a function. So let's suppose G1 and G2 are groups, but I'll let phi be a function. All right. Now, this is most interesting in the case that phi is a homomorphism. But if phi is a function, I can still define these. First of all, the kernel of phi is going to be x in G1 such that what? Such that phi of x is equal to E2. And 2, the image of phi is going to be phi of x such that x is an element of G1. So kernel and image are really important for a homomorphism. Let's see here. I can rewrite this both. I can write both of these in terms of images or inverse image of sets. All right. In particular, this is exactly the inverse image of the set containing E2. These are all the points in the domain that map to E2, right? And in terms of images of functions, the image is literally the image of G1. I mean, it's, okay, well, whatever. It depends on what you know, but it is phi of G1 is a compact way of expressing the same notion. All right? So, trying to keep myself on the path here. So there's a theorem which says the following: if we have phi from G1 to G2 a homomorphism, guess what? Then the kernel of phi is a subgroup of G1, and the image of phi is a subgroup of G2. Proof. Left to reader. I will give you an example. If you took my linear, I proved that theorem in the context of linear transformations, where we proved that the kernel and the range were subspaces. Right? That same theorem here becomes the homomorphism has a kernel and an image are subgroups. The proof is almost identical. But anyway, so an example of this, right? If we look at what's the kernel of phi 3? So you guys tell me, what does this mapping phi 3 send to the identity? What's that? Everything what? AN, right? Is that nice? So what this says is if you can exhibit a homomorphism which takes a given subset as its kernel, that proves that subset is in fact a subgroup of the group. That is a fantastic way to prove something is a subgroup, right? As a very nice way to show things are subgroups. Anyway, so there's that. Proposition 2 is the following. If we have a homomorphism, G1 to G2, a homomorphism, then phi is 1 to 1. Let me say injective. If and only if, let me use the double arrows, if and only if the kernel of phi is equal to the set containing the identity. It's of course the identity of 1. All right, this I will prove. First of all, look at this direction, right? So what we're going to do, suppose phi is 1 to 1, right? We need to show that the kernel of phi is just the identity element, right? Observe, I can't spell observe. Observe phi of E1 is equal to E2 by prop 1, right? Thus, E1 is an element of the kernel of phi, right? So it's in there. Now what? Suppose x is an element of the kernel of phi, right? Then what's that say? That says phi of x is equal to what? By definition, E2, right? But by the way, that's equal to phi of E1. Therefore, by injectivity, we have what? X equals to E1, right? But x is arbitrary, right? So we've shown that every point in the kernel is the identity 1, right? Therefore, I just use it therefore. Let me use it thus. Thus, the kernel of phi is equal to the set containing E1. If people get carried away, sometimes they omit the curly brackets around E1, but we really shouldn't, because we're trying to be careful. But I admit, sometimes it bothers me to write these, but you know, I should write those. For now, I'm going to write those. I'm going to continue writing those, at least in this course. All right. Now that's only half of it, right? The other half, I'll write over here. So now we do what? Assume that the kernel of phi is equal to E, right? I want to do what? I want to show that phi is injective. So suppose phi of x is equal to phi of y for some x and y in G1. Right? Now, I need to get to the identity. And I'm sorry, I forgot my E1 here, right? Okay. So what I thought to do, I mean, there may be other ways to do this, but it's if I multiply by phi of, let me just look at my notes for a second here. What did I multiply by? Phi of x inverse, yeah? What does that tell me? So over here, by the homomorphism property, I have phi of x inverse x, right? And over here, by the homomorphism property, I have phi of x inverse times y. Right? X inverse times x is what? E1. But I know that phi of E1 is what? Is E2 by proposition of what? Prop 1 from today, right? And so what does that say about x inverse y? Right, that says that x inverse times y is an element of the kernel of phi. So therefore, but the kernel of phi is equal to the set containing E1, right? So that says by set theory that x inverse y is just equal to E1, which of course then multiply x on both sides, we get y equals to x. Just to conclude, that shows what? Phi is 1 to 1, right? So we've shown if and only if. Again, this is really pretty fantastic. If you want me to tell you if a real function is 1 to 1 everywhere, I can't just find out what happens at 0. Right? I have f of x equals to x squared, right? I have f of 0 is equal to 0. So the kernel of f, with respect to the additive group of real numbers, is 0. And yet, this does not imply that f is 1 to 1, does it? Because we know that the graph looks like this. F is not a homomorphism of the additive group of real numbers, right? This theorem does not apply. Injectivity is not so simple as looking at what maps to the identity for something that's not a homomorphism. Homomorphisms are special. Generally, the problem of figuring out what mappings are injective is a pain. All right. Finally, you're like, I thought this was about isomorphism. Fair enough. You got me. So here we go. Surf. I was about to write surfjective. Good job. In other words, if it's 1 to 1 and onto, right? In other words, sorry, my box is losing its integrity. So a isomorphism is a homomorphism, which is also a bijection. So I guess my immediate question to you is, of the 3 homomorphisms we've looked at today, is any, and by the way, this is consistent with our use of the word isomorphism in linear algebra, right? A bijective linear transformation is an isomorphism. So, but there's a little bit more structure in linear algebra. And the term isomorphism is more general than group theory. All right? It's a term which transcends different fields of mathematics. There is some unifying notion of it in something called category theory, but if you want to ask, don't ask me about that, ask Nathan Bedell. Let's see here. He cares more. Let's see here. I do care about category theory, just not as much as Nathan does. Like, Nathan brings it up in the context of other unrelated conversations. He truly loves it. Let's see here. So is any of these a isomorphism? By the way, while you're thinking about that, if there exists an isomorphism like this, then we say that G1 is isomorphic to G2. Intuitively, they're the same group. They just have different notation. They have the same structure as groups, really. So guys, what do you think? Well, let me help you out here. Phi3 is definitely out. The kernel of Phi3 is AN, and this is most certainly not equal to the set just containing the identity permutation, right? At least for n greater than or equal to 2, we're definitely out of luck there. So let's just make it, just to be clear, okay. Definitely not injective, right? In fact, this is a 2-to-1 map. This one, goodness gracious, you know, is this a 1-to-1 map? If I tell you the determinant of a matrix is 3, is there just one such? No, there's lots of different matrices with the determinant 3, right? This is also not 1-to-1. So you can see the kernel of this map is not. In fact, the kernel of this map, what's the kernel of Phi2 while we're at it? What's the multiplicative identity in the what's multiplicative identity in here? No, you hurt me with that. This is a field, non-zero elements in the field. You could fix this, make me feel better by saying I meant 1-by-1 matrices. Okay, no, it's fine. The identity in, like, what's the identity in the real numbers? Non-zero real numbers. 1, right? So we're looking at the set, right? So in fact, this is what's known as SLNF. Oh look, SLNF is a group because it's the kernel of that homomorphism. All right, I guess if this is going to be an interesting question I asked, we better hope that E1, example 1 was an isomorphism, right? Is it? What's the kernel? In other words, if we look at the kernel of Phi1, right, what is that? Right, it's x such that e to the x is equal to 1, right? And that's exactly, of course, just the set. That's just 0, right? Only 0 maps to 1 under the exponential. Is the exponential a surjection? Is it onto the set of positive real numbers? So you pick me a positive real number, right? Y an element of 0 infinity. Then I give you Phi1 of the natural log of y is equal to e to the natural log of y, which is y again. There you go, proof. It is in fact a surjection. So it's a bijection, and we already remarked that it preserved the operations. In fact, there you go. That's an isomorphism. There's an isomorphism between the additive real numbers and the multiplicative group of positive real numbers. And that isomorphism is the exponential. Okay, so there's a couple. Other maps on G, generic. So one thing I would point out to you is if we say phi is a mapping from G to G, all right, with phi of x equals to x, right, for all x in G, then what is this? I mean, do we have phi of x times y? Well, that's x times y, right? Which is phi of x times phi of y. Right? So it's operation preserving. Is it onto? Well, if G is in G, right, then we have what? Phi of G is equal to G, so therefore phi is onto. Okay. These are not hard. If phi of A is equal to phi of B, what's that tell us? It tells us A equals to B. Okay, fine, it's 1-to-1. I mean, this is dumb. My point is, this mapping is a bijection. It's operation preserving. What is it also known as? This is the identity map, right? So I usually, you say id G or something like that, is an isomorphism. So this shows that any group, right, is isomorphic to itself. Okay. In fact, we can also prove that the inverse of an isomorphism is an isomorphism, all right? And we can prove that the composite of isomorphisms is an isomorphism. That will show that if a space G1 is isomorphic to a space G2, then conversely the G2 is isomorphic to G1 under the inverse map. And then the fact that the composition of isomorphisms is once more an isomorphism will give us that if we have G1 is isomorphic to G2, and if we have that G2 is isomorphic to G3, it follows that G1 is isomorphic to G3. In other words, isomorphism is an equivalence relation, right? So you can look at all groups, and you can look at the isomorphism equivalence classes of these groups. Everything in one, all set of all groups which are isomorphic to a given group, in some sense, are the same, right? They're not the same as point sets, but they have the same group structure. So here's another mapping we might look at. Some of those things I just said seem like good homework problems. Let's see here. LG, not to be confused with the electronics manufacturer, mapping from G to G, although Gallian uses T sub G for this, which I guess means transformation by G. Whatever, I'm going to use L sub G because I want L sub G to mean left multiplication by G. And so here's the definition. L sub G of x is equal to Gx. If your group had, if you were working with G star, then your L sub G of x would be what? It would be G star x, okay? So this is, but I'm going to keep talking in juxtaposition because it makes what I'm saying go so much faster. All right, so this is left multiplication map. Is this an isomorphism? It's definitely a mapping, right? How do I know that this mapping is well defined? G times x. How do I know that that's an element of G again? Definition of a what? Which definition? Of a group, right? Yeah, the group operation is closed, right? The product of two group elements is once more in the group. So that's how I know it's into G. But I actually don't think it's an isomorphism, right? Because first of all, it's not operation preserving. Check it out. LG of x times y would be gxy, right? Would this be equal to, question mark, LG of x times LG of y? Probably not, right? Because this is going to be equal to gx, gy. Why would those be equal? Unless what? G is the identity, right? If G is the identity, and then we have L sub E of x, which is what, equal to EX, which is equal to x. Therefore, L sub E is equal to the identity on G. Right. So left multiplication maps, maybe not isomorphisms, but they're actually useful. So if we look at the set, what do left multiplication maps do, though? Let's study their properties a little bit more. So let's look at what happens if we take LG composed with LH and act on X. That would be like LG of LH of X, right? Which would be LG of HX, which would be GHX, which would be what? Now, to get from here, I mean, to be clear, to really get from here to here, we need associativity. Because if you think about it logically, you know, on the one hand we've got GHX, and then I have to rewrite it as GH times X, right? So associativity is mission critical right there in order to make that last step. Now this holds for all X. Am I right? To quote a certain venerable cartoon character, believe it! So this holds for all X. In G, therefore, the functions LG composed with LH are equal to L of GH. Well, that's cool. What's the relation of LG and LG inverse? Well, using this identity we just derived, it's L of GG inverse, right? Which is L of E, which, by the way, is the identity mapping on the group. So think about the set of left multiplication operators. Let's let S equal the set of left multiplication operators on G. I believe Gallian just calls it G bar. Okay? What can we say about this set? If you take two things in the set, right, and you can compose them, what do you get? If I take LG and I take LH and I compose them, I get L of GH, which is again what? An element of the set. With respect to composition, the identity's in there because it's L sub E, right? With respect to inversion, if LG is in there, LG inverse is in there, and it serves as an inverse, left or right. And it's associative with respect to composition. In other words, this is a group with respect to composition. And if you look at this, if I say phi of G equals to L sub G, all right, and you check it out. So if I look at phi of GH, right, well, that's equal to L of GH, which is equal to LG composed with LH, which, by the way, is phi of G composed with phi of H. What's that show? It's operation preserving this mapping phi. Where's phi going from? It's mapping from G to G bar. It's operation preserving. What's its kernel? In other words, phi sends, what's the identity over here? It's the identity map, right? How do you get the identity map? There's only one way. It's E, right? So this is E. Therefore, phi is in 1-to-1. Is it onto? You give me anything here, right? It's onto by construction, essentially, right? If L sub G is in G bar, then phi of G is L sub G, so it's onto. So it's onto, it's 1-to-1, it's structure preserving. It is an isomorphism. This is Cayley's theorem. What does Cayley's theorem say? It says that G is isomorphic to a set of permutations, and I actually showed you what set of permutations. It's isomorphic to a set of permutations of just functions from G to G. Just like that. So any set, any group is isomorphic to a set of permutations in this way. This? Left? Did I say left? Oh, yeah, I did something funny there, huh? Yeah, I'll do that. Anyway, sorry I don't have the notes typed yet. I felt bad again. So I'm working on them. I will assign you something to do to turn in Wednesday, right? I'll do that first and write the notes second. In the meantime, read Gallian. He's pretty good.